Okay, we'll continue with a few more questions. We have about 30 minutes to go to the top of the hour. Are there, before we start with more questions from my list, are there any questions at this point from the audience that we should address? Yes, please.
Hi, good morning. I am a quality and technology manager in a foundry now, and I heard that you are putting requirements on the tests, for instance, for leakage of valves, saying that you're going to test the valves at 196 minus degrees Celsius, but that will be for the leakage tests, right? So when it comes to material properties instead and chemical composition, does the new revision of the international standards change also the requirements of mechanical properties, or will it be the same as before?
I know you addressed part of that in your work for your standard.
Yeah, we can talk about the API 6D, which is not meant for cryogenic valves. It's really for gas only. So the same requirement that is valid for natural gas is also for hydrogen. So if you go low in temperature, whatever the temperature on your nameplate, you must have confirmed that the material is suitable for that. So that can imply some impact materials, but impact tests, sorry, on low temperatures. But there's no specific requirements because it's not part of the scope of the document.
On the cryogenic side?
On cryogenic side is easier because there is practically only one material, 316 or 304, so it's very simple. There is no special requirement except for the CHRP. The CHRP test that for 316, 304 is not a problem, taking consideration that many valves use high strength material for stem. That is different because if you don't use 316, the CHRP test is necessary to perform the CHRP test a lateral expansion. And just an example, Nitronics 50, the typical Nitronics 50 that we can find for the standard valves that we call high strength or super high strength, are not are good in terms of CHRP, more or less stay around 50 joule, but for lateral expansion could be not so good. It's necessary to test anytime this material. The best solution should be select this type of material in a needed form. Like there is another material, Nitronic 60, that is not upset is not an ACE, but that is good also for cryogenic. It's quite used in cryogenic. But Nitronic 50, that probably is better in presence of H2, is necessary to check both. Because if the CHRP is lower than 50 joule, probably the lateral expansion is not zero. The B31 3 ask 0.53 millimeter. It's not you do not achieve this number. You stay below, so it's not acceptable. This is the only point.
So these nitronic grades are intended for stem applications?
Stem, yes, stem.
Yes,
for other
body.
part of the valve
Yeah,
is
no,
316
yeah,
or CF3M. So it's not a big problem.
Yeah.
But anyways, mainly when you use the cast body, it's always better to perform the HRP, always, also in 316. Okay. 254 should be better.
Okay. Tom, on the subject of material specifications, do you have any other comments you could offer?
For cryogenics, the soft seats are typically Teflon or some sort of PTFE. As you said earlier, 304, 316 are the standards for the metal part of the valves. but it's the soft seats that are probably needs further development because of issues with some of the soft seats that are under higher pressures and moving.
And regarding STEM materials, any insights there, or are those typically austenitic as well, similar to the bottom?
Yeah, they're the same thing. And typically for a cryogenic valve, you have to have an extended stem because the packing has to be away from the cold to create a warm gas barrier. So the packing material is important as well on extended stem valves. Almost all cryogenic valves are extended stem for this reason, and also to keep the valve handle out of the ice growth, which occurs on cryogenic systems that are in service continually.
Very good. Thank you very much for that. Another follow-up question, please.
Yeah. Hi everyone, I'm Christian Salvatori from Victrex. Just a quick one. It's more a curiosity, and I would like to get a feedback from the gentleman here regarding. So, as a producer of material, we have various feedback from various markets, but I would like to understand what's your impression in the oil and gas, and especially in the hydrogen field. We are developing new materials now, and there is this PFAS-free requirements in general, which has different sense of urgency depending on the markets. Can make an example, in food and pharma, it's quite urgent to find PFAS-free alternatives. What about the new materials that we might develop? We are already developing for the cryogenic applications like CryoPeak, etc. But what do you think is going to happen for new materials to be developed in this industry? Should they be? Do you expect them to be PFAS-free, or do you think this is not yet a hot topic and yeah, it's not urgent like in other markets?
That's a good question. It's a tough question too.
Probably.
I can say from my perspective, I'm not seeing an urgency, any greater urgency in the hydrogen applications that I know of with regards to PFAS, that concern, that whole complex situation, any different than any other valve application domain. But you bring up a couple of obvious examples like food and drugs would be pretty critical. But in general, when it's talking about hydrogen as a fuel source, I wouldn't think it's the same degree of urgency or concern. But that's just me expressing an intuitive opinion, not based on the actual experience.
Yeah, I also don't think it's a matter for the valve specifications. The valve specifications are there to set minimum requirements for performance. And if there is a regulation that there's an introduction for PFAS-containing materials, I don't think that will be covered by the standards. That's a separate regulation. That's my feeling. It's my personal feeling.
There's one other thing I'm going to say in terms of use of PFAS in sealing solutions, in particular stem sealing, in elevated hydrogen service, elevated temperature hydrogen service. And it is that at those high temperatures, PFAS won't survive. Like anything containing PFAS won't survive. So there's a fairly decent body of knowledge and experience, operating experience, that at elevated temperatures, I'm going to say 500 to 600 C, you won't see PTFE containing packing materials being used in the valves. But you also won't see an epidemic of valve failures where hydrogen is being handled by the valve. And there are, I'm sure, manufacturers in-house or in this room that have that particular experience, and they're not particularly concerned about leakage at the packing because of the absence of PFAS containing substances.
And Christian, you can probably explain this better than myself, is actually in the making of the polymeric materials, it's at the front end that the concern is. That's where, the dangers are for human and contamination and the rest. Is that right?
Yeah, I think it's a complex field. It's certainly not my area of expertise, but I have listened to a few presentations by people who are expert in it. And yes, you bring up the point of, let's say, PFOAs being used in the process of manufacturing PFAS compounds. And even that has a nuance, because depending on the source of the PFOA substances, there are or are not concerns. And and then there's the notion of polymeric versus non-polymeric PFAS substances. And I think it's a very fluid situation right now, and the regulators, the legislators and the regulators are, let's say, at different levels of education and awareness and knowledge as to the complexities. So I think we will probably be, in the hydrogen applications, be equally affected as any other part of the industry will be. But again, the good news I can say is we don't necessarily rely on PFAS substances for at least a range of the application, but I think on cryogenic that wouldn't be necessarily the case. Anybody else have any other knowledge, insights on this? No. Okay. And we're talking about fugitive emissions, so I'm going to ask ourselves one other question on this. How does hydrogen differ from greenhouse gases and VOCs with respect to fugitive emissions, impact, and reduction? And what are some of the key considerations in qualifying valves for low fugitive emissions in hydrogen service? And I know that that's been addressed in Annex M, and it's going to be something that we're going to be looking at as well. So,
yeah, as mentioned in the introduction, we're talking about fugitive emissions because that's a standard that was originally developed for fugitive emission for methane, and it's now starting to be adopted for other reasons. So we're not that much concerned for fugitive emissions of hydrogen. We mentioned it's an indirect greenhouse gas because it retains the methane longer in the atmosphere. But the major concern is about potential fire or explosion risk, that if you do have a leakage to the environment, and if there is ignition and all these elements are combined, then you have a potential hazard. So that's the reason why, indeed, in the Annex M of API 6D, we put requirements for fugitive emissions. We test that with helium as part of the design validation test. And as part of the production test, you can test it either with helium or with forming gas. Because we wanted to avoid too much use of helium, at least give the possibility of testing it with another gas.
thanks for that. And I can say that on the MSS side, when we look at the cryogenic testing requirements, there isn't an intention to have an extensive additional qualification done for fugitive emissions. We're going to rely on existing fugitive emissions qualification, most likely ISO levels, and those are so far being deemed as adequate for the hydrogen service that we expect to see. But again, on the cryogenic side, I think ISO would be appropriate, right? Yes. Yeah.
But you would say that safety is more critical than emissions when it comes to hydrogen.
Oh yeah, yes. I mean, excellent point. Excellent point. Yeah, that's a key issue. It's not the same concern from a greenhouse gas or VOC point of view. It is about the safety. It's about avoiding concentrations of hydrogen buildup that could lead to ignition. And Tom, I know you have some direct knowledge as to how to be concerned and deal and address that. So if you have any comments on this point, it would be much appreciated.
Could you summarize it again? I'm having difficulty hearing a lot of.
Sorry, I'll summarize again. The topic is fugitive emissions or escape of hydrogen from the valve pressure boundary, and the safety concerns, as opposed to the, let's say, pollution concerns of the escape of hydrogen into the environment.
Yeah, I did hear, a discussion around indirect effect on the environment for the environmental piece of it. And that is what I've been involved with and heard about as well. But safety, as we discussed, is a big problem. But leaks on hydrogen systems are typically very small, and they start small, and they need to be caught small. So maintaining mechanical integrity of the system is important from startup through operation, including, frequent checks of leaks around mechanical boundaries, the packing, the seals, those type of things. Because again, hydrogen leaks are typically smaller to begin with, and the larger catastrophic leaks are managed through correct design, correct maintenance of the equipment, etc. So the smaller leaks, as long as you stay out of the flammable range, which is 4 to 74%, they're not really an issue. And plus, there's a requirement for a certain amount of flow of hydrogen to maintain ignition. So the biggest issue with the valves is, as was said, I believe earlier, that it's capturing the hydrogen, indoors especially. So outdoors, small leaks, they occur. It's just a matter of managing them from a maintenance standpoint. Larger leaks you want to minimize by managing the smaller leaks and managing the designs correctly.
Great. Thank you for that. Any follow-on questions with respect to fugitive emissions and external leak of hydrogen?
I'd like to ask Tom a question.
Sure, go ahead.
Tom, this is Greg Peterson. I'm on the panel as well, and a question around we talked about fugitive emissions, I know, but when we kind of went to safety, you mentioned the refueling stations in California, and I was curious when we come to practical applications of hydrogen, and we're trying to scale it for human consumption. What is the state of the hydrogen when it's getting to these refueling stations in California, and then what are the applications that they're using it for? It's just curious. If you had that
the refueling stations, I'm not sure about what other application, but refueling stations are using gas. Nobody's fueling with liquid hydrogen yet. That's mainly starting with larger equipment like locomotives and large mining equipment, et cetera, like LNG is used for. But even with liquid systems in the California area, it's compressed as a liquid and then stored as a gas and then fueled as a gas. The emissions are fairly low because they do have a valve where there's no purging requirements when they connect to the vehicles. It's a no purge valve. So the losses are fairly low for gaseous. Liquid hydrogen losses are much higher. Liquid hydrogen losses have been estimated between 10 and 20% across the system. Any cryogen is a use it or lose it. So once you put it in the container, unless you use refrigeration, which is almost unknown at the customer sites, at the plants, that's a different issue. The hydrogen has to vent eventually. And so there's a lot of losses around liquid hydrogen as compared to gaseous systems. There's many other applications that use hydrogen from, heat treating, industrial applications that are very diverse. There's many areas that use hydrogen. Hydrogen is actually used in power plants for generator cooling. There's a lot of hydrogen used in the world today in the industrial area, and it's beginning to enter the commercial market for fueling vehicles. And that's really the biggest application for most of the public. Does that answer your question?
I think.
Yes, it does, Tom. And so when we talk about scaling it, I was referring to the gentleman that asked the question about the hydrogen coming up to the residential area. Would we anticipate that would be a blended hydrogen, blended with natural gas, and are they using this hydrogen in vehicles? Is it just hydrogen, or is it a blend?
No, it's pure hydrogen. They fill it typically at 350 bar or 700 bars. You're actually going to semi-trucks as well. So a lot of the tractors are being built for over the road for hydrogen, and that's where the Department of Energy has been developing a hydrogen hub structure across the U.S. where hydrogen is going to be used much more than it is today in these refueling areas, and then those for trucks as well as cars.
Thank you.
Sorry, Tom, we are having a bit of a sound quality issue. It's not your fault. It's just the transmission. But we are getting most of what you're saying and getting the gist of it for sure. Thank you very much. Well, I think I want to just open the floor one more time to any additional questions because we're coming to the end of our prepared questions. I have one or two more, I guess, if the panel's ready for it. But I just want to make sure we address any other questions from the floor. No? Okay. All right. Well, I'll ask a... Oh, is there one? I'm sorry. Tony? Sorry. Go ahead, please.
I just want to go back a bit. when we're talking about material requirements, we've heard problems with permeation, embrittlement, blistering. What other knowns do we know about the effects of hydrogen and the consequences of those effects on the material integrity? And I guess that will change between, it will change between metallic and non-metallic conditions. Are there other knowns that could lead to, the material becoming in an inferior state, basically?
There are knowns, but there are more unknowns, I guess. This is probably the answer.
Then what are we doing about the unknowns?
I guess adapting the standards as we discover. So there are a lot of testing going on by a lot of different institutes, independent. A lot of companies are working on that. I personally can only hope that will be made public so that everybody can benefit from those answers to that. And the way I see it is that in, for instance, the API 6D Annex M, we've been a little bit conservative. Okay, it's also limited to class 2500, whereas at higher pressure classes we see different things coming up. So there's more unknown, I think, in the higher pressure classes, and the higher temperatures and the lower temperatures as well. So with API 6D Annex M, I think we're pretty safe for the moment. But as we discover in the future, we will probably adapt, and maybe we will make the requirement less stringent than they are currently written.
So have we got groups of material specialists supporting the development of the 6D work?
Not 6D, but within the API, there are tests being carried out right now, both on soft materials and metallic materials.
Right.
So that's one of the sources. But I hope that in the industry there are many more tests going on at different levels.
Right.
And what I just mentioned, I hope that will be made public so that everybody can benefit from that as well.
Fantastic. Thank you.
I'll add on to that. So within API Subcommittee 21, within the CSOEM group, has both a metallics and a non-metallics group studying specifically for hydrogen. And I do think that one of the things that I think has been well discovered in the past few years is along the lines of explosive decompression. It has been well documented that CO2 is a more aggressive gas for explosive decompression than compared to hydrogen, which is good news to us in the industry, because if you've got non-metallics that have been proven for ED resistance, RGD resistance in CO2, then they're deemed to be fully acceptable for hydrogen. So a slim glimmer of hope of things that are well known in this anyway. So.
You bring up an excellent point, Tony. I can say I participate at ASMEB 16, and I'm on the MTC, the Materials Technical Committee, and honestly, I got to tell you, I don't think I can recall much discussion centered around hydrogen applications. So note taken, and I'm going to make sure to bring it up the next time I attend one of those sessions. Thanks for bringing it up.
There's also work being done by the national laboratories in the United States, NREL, Sandia, et cetera, that are also looking at materials and the effects of hydrogen on those materials.
Thank you, Tom. More question? Great. Is there? Okay.
Maybe something to add to the impact of hydrogen on materials. So my name is Ruth Jakowiak from DuPont. One aspect that's known is it can impact the tribological properties of materials as well. So as hydrogen can act as a lubricity enhancer, and that makes testing materials in liquid nitrogen difficult to judge how the performance in liquid hydrogen is going to be, just as a remark.
Can you clarify again, how does it affect the behavior or the mechanical properties, I should say?
Depends if you have a metallic or non-metallic materials. So for non-metallic materials, hydrogen can penetrate, interact with the chain mobility. It can interact with graphites or with fillers. And the absence of an oxidized metal layer that is used for tribological enhancements with plastics is missing in hydrogen, and that has an impact on wear rate and friction propagation.
Where you're trying to achieve good tribological properties, they can be degraded by the presence of hydrogen.
It can be improved, actually.
Oh, can be improved.
It
Okay,
can be
that's
improved.
what I was trying to
It
clarify.
depends on the material combination.
So it can go both ways.
It can go both ways.
Okay, interesting.
And
Great,
that makes
good to know.
it challenging for us to determine how a component operates when it's been tested in liquid nitrogen, when the lubricity effect of hydrogen is, for example, missing.
So that means that you really have to get down to the idiosyncrasies of every combination and understand
Yes.
them individually and characterize them one by one, in a way.
Ideally,
Yeah, if you can.
and test in hydrogen, but we understood it's difficult, and
That's a good
safety
insight.
requirements are challenging to do so.
That's good to know. Any other questions or points? Yes, sir.
Good morning. I'm Abul from Actuation Lab. Yeah, I had to take the time.
Yeah, you're good. You're good.
We are Actuation Lab in the UK. We have a stemless valve technology. My question is regarding the natural gas blending in the pipelines in the US versus the tolerance in the UK and European nations. So why is the stark difference? Is it under 2% in the North American regulations and then about 20% in the UK and Europe? I just wanted to understand why is that stark difference in between the two regions?
Joe, could you repeat the question? I missed part of it.
There is apparently a very significant distinction in the North American and the European regimes as to the concentration or percentage of hydrogen in a natural gas stream that constitute hydrogen service, 2% in the US, 20% in Europe. Am I interpreting
That's
the question
right, yes.
correctly? And what
Yeah,
explains
that's
that?
actually been changing. There's companies that are testing at 20%. And at PA2, we're actually looking at going up to 30% potentially hydrogen. The big concern is the embrittlement in the existing pipelines. That's probably by far the largest concern. Additionally, there are other concerns with the joint sizes, especially mechanical joints, and leakage rates of hydrogen once you get over those. So it's being studied, but there are companies that are involved in the U.S. natural gas companies that are running at 20% some of the internal testing. So that's where it is going, and I know the UK has been doing that for a while. So that is being managed.
So it's trending upwards, and in other
Yes.
words, the confidence level in allowing higher concentrations of hydrogen is increasing to the point where higher concentrations are tolerable or becoming more tolerable.
Yes.
If I can add a little bit to that, I think the older concerns are what about the appliances? So whoever receives that gas, can they handle that blend? Also, what I understand, the 20% limit that we hear often in Europe is limited to the compressors. Above that, the existing compressors, they cannot compress the gas if the percentage of hydrogen is higher than 20%. So that means if you want to transport blends in an existing pipeline with existing compressors, that's the limit. If you go beyond that, you need to exchange all the compressors. Then I believe there are also differences of opinion between the different countries. So then you get the interstate or inter-country limits. So that all those, let's say, the network points are being looked at as well, what the limits are. But I cannot explain why there's a difference between the US and then the UK, to come back to your original question.
I understand. Thank you very much. And Tom, are we expecting to see higher percentage of concentration coming up in the natural pipelines in the US and North America as well in the future?
Yes, I believe so. That is the trend.
Okay, great. Thank you.
Thank you for that question. Any other questions? We're coming near to the end. I guess I have one or two questions still unasked, so I'll use them up if I can to get us to the top of the hour. Among the various hydrogen production technologies in use today, which include steam methane reforming, electrolysis, coal gasification, biomass gasification, and ammonia cracking, and emerging technologies like photoelectrochemical water splitting, do we see any dominant technologies in the medium and long term, and to what extent do those differences in technology impact valve selection design and so on? And maybe a special point on ammonia cracking, we're seeing it taking a prominent role currently in Europe with some projects going on. Do we see this as taking a dominant position somewhere in the supply chain of hydrogen? And again, does it affect? How does it affect? Let's say the specification, selection, and qualification of valves. It's a very big question, very broad question. That's why I held it off to the end.
How does it affect the different processes? I don't really think that it does. I mean, hydrogen is hydrogen, so how it's produced really doesn't affect the properties or the of what the valve needs to cover. It's a valve in one process is the same as the others. Yeah, so that's it in a nutshell there.
Yeah. Okay. Please, if anybody else has any other comment on that, please.
Question about the ammonia.
Well, ammonia amongst others, but there are several, predominant technologies used for the production of hydrogen. To what extent do any of them play a role in the?
No, and the ammonia's been around for many years. Use it as an agricultural fertilizer, so its effect on steels is well known as well. So whether you're talking ammonia use in valves and steels, a lot of post-weld heat treat and, the storage vessels or pipelines and valves. So, that's established technology to go from, use of materials, even low-temp materials, not the stainless steel materials, but the low-temp carbons in ammonia service, so.
Yeah, I'll just say I'll answer the question myself. We did discuss these questions, of course, ahead of time, and the consensus view, and I bring it up only to sort of add to the discussion. The consensus view is the production method. It doesn't really directly have the impact on the valve sizing, selection, qualification, and so on. It is the individual application that is going to define the needs for the valve, and it shouldn't, as I pointed out early in the presentation, the colors of hydrogen don't make a difference they themselves don't define what type of valve or how, what type of valve you use, how you test it, how you qualify it, how you build it, or anything like that. It's more what that valve will actually see in terms of its immediate service that defines it. So just to avoid getting confused on the subject, the source of the hydrogen isn't the factor.
Well, if I may add, I agree with all of that for the existing technologies, but we see a lot of emerging technologies, and there will be new technologies coming up for the way of producing hydrogen.
Yes.
So the steam method forming, so all those they're existing, and I don't see any change coming. Also in regulations, because it's so well proven already. Yeah. But pyrolysis is a new upcoming technology, more and more. But even electrolysis, I mean, you need valves for that as well, somehow. Yeah. Okay, so then you get in different temperatures, different pressure classes, and maybe different types of valves as well. So I think what is known, yes, there's no change, but I think we need to look out for these emerging technologies.
Good point. Thank you.
Yeah, and as far as looking out for the emerging technologies, the valve design is based on the design parameters: the pressure, the temperature, the composition of what's in there, the leakage allowed rate. So those are what really drives the design, and the new applications will probably stretch those limits that we have today. So that's going to be the issue, is managing when these new designs pop up, where do the flow parameters change? And how do we address those with the valves?
As in the Purge example that you talked about earlier. We've made it to the top of the hour. That concludes this session. I want to thank and congratulate this excellent panel for the information and wisdom they've shared with us today, and I want to thank this audience for your interest and your participation and for your questions as well. Thank you very much, everyone.